we consider today an important aspect of machine design, that is engineering materials. So, this lecture is lecture number 3 and we will be talking about, as I told you, about the engineering materials. Now, you can see the choice of material for a machine element is very important. In the earlier lecture of the design philosophy, what we have seen that what are the concepts and what are the ideas one should have for a machine element design. However, to design a machine element, of course, you require a material which will serve your purpose. So, for that reason, the choice of material for any design of a machine element is of the utmost priority. Now, what we can say that basically the choice depends on 3 aspects. One is property of the material, another is the cost of the material, another is the availability of the material. Now, property, you understand that basically whenever we are designing a machine element, then the machine element will be acted upon by various types of loads that you know. Now, the material should be such that it should withstand those loads without failing. Now, in this regard, what happens that when you talk about the failure, very grossly we consider that what is the material property normally at the elastic limit. Anyway, we will be considering all these material properties such as elastic limit, what I have just mentioned, in details after some time or maybe some other lecture, but one thing you understand from the basic your understanding of the mechanics, that you know the material properties means that one of the important thing is that elastic limit, that means beyond which if the material goes, then it has have a plastic stage, means the material deforms. So, normally what we consider in machine element design is that the material is not failing, means material is within its elastic limit, and to be more precise we call that point as a yield point. So, each and every material will have this type of properties. Now, not only elastic properties, in certain cases you require how much is its plastic deformation, how much it is the surface finish you can have, how much its malleability. All these things are very important in the design of this particular choice of the materials when you are going for a design of a machine element. Of course, after you make a machine element, this particular product has to be marketable, has to be marketed, or it has to be sold off. So, obviously, the manufacturing costs becomes a very important aspect for any machine element design. So, the cost of a particular machine element is very much dependent on the type of material. Well, one of the situations may be that say iron, wrought iron or a mild steel or something like that, which is very commonly seen in all machine elements, has to have a some amount, some values, so that the product becomes actually cheap or something like that. But at the same time, what happens that in certain cases you cannot use those materials. Suppose you want an environment where there should a machine element to be used in an environment where you do not want any rust to be taking place. So, suppose by some means the choice of the element becomes stainless steel, you know that is a very good material for corrosion, etc. So, in that case obviously the material cost becomes higher compared to the material what we have earlier chosen. Anyway, those cases are inevitable. However, the basic idea of talking about the cost is that one has to optimize between the use and the material cost. Okay? That means all materials cannot be used just looking at their cost. Sometimes for that reason one machine element could be costlier than the other, and the primary situation comes out to be of the material material cost. Of course, other situations like manufacturing considerations also do account for the cost of a machine design. Okay, design of a machine element. Okay. So, once we consider the properties, once we consider the cost, the third point, as you can see, is noted on the slide as an availability. So, you are very ambitious, developed a beautiful material who has got a beautiful property, beautiful in the sense for the particular design you are going to make. Everything is nice, its cost is also something reachable, within the reach of the people, but it is not available readily, it is not available in the market. Okay, it takes a very long time for procurement, and thereby it may so happen that your idea could still remain in ambitious stage. Okay, because all situations like the design has got two economic considerations, one is cost, another is also time. Because if you are going to make a machine element, as because the material is not available and you are waiting for years after years, that won't be good for you. Okay, the sellability in the market will fall. So, I think from our general idea, intuitive idea, we can understand that what is the importance of a material property first of all, which is of course the primary requirement, then comes the cost and the availability. So, to summarize this idea, that means we have to choose a proper material for machine design, looking into the aspect of properties, costs and availability. Next, you can just look after this particular slide, which defines common engineering materials. Now, although there are various materials available and the list is never ending, but here what we will be considering, as you can understand, common engineering materials, which means that we will be concentrating on those materials which we see in everyday life used as a machine as manufacturing of the machine components. Now, if we consider common engineering materials, you can see that there is a broad classification. One, we consider ferrous metals, another are the non-ferrous metals, and another's are totally non-metals, okay, like say timber, glass, ceramics, etc., which are the non-metals. The most common use is ferrous materials that you understand. Also non-ferrous metals and non-metals are quite used in design of the machine elements. And for all the three types of materials, namely ferrous material, non-metal and non-ferrous metals, non-ferrous metals, the one of the important thing comes out to be the mechanical properties. As I told you in the earlier slide, that first thing is the mechanical property. Whichever the material you choose, one has to look for that one. So, in this particular discussions on engineering materials, we will have a look at the types of ferrous metals that are available, types of non-ferrous metals that are available, which are the important non-metals, and for all those things, what are the important mechanical properties that we come across in the design of machine elements, that also we will discuss. So, we start the our idea or start the descriptions of the ferrous metals which are commonly used in engineering. Now, if we look once again, what are the important ferrous metals? The important ferrous metals are cast iron, another one is wrought iron another is a steel. So, this has got an basic components of iron, but due to the compositions and mixing of some other elements, what happens, the name comes out to be along cast iron, wrought iron and the steel. See the cast iron. What is an cast iron? These cast irons are the alloy of iron, carbon and silicon. These materials are, as a matter of fact, as it is been given over here, you can see is quite hard and brittle. By now you have some understanding of the brittle, means normally the brittle material do not have much of the plastic zone. That means it is only applicable in the elastic zone, and then it do not elongate, that means it do not have any plasticity character. So, that is we called as an brittle. So, if you have got a certain amount of plastic zone, means it covers some amount of plastic zone, then we will normally call that materials as ductiles. That you have already heard, I suppose. Now, one of the characteristic features of this particular cast iron is that it has a good amount of carbon content. This carbon content is ranging from something around 1.7% to 3%. Now, in which form the carbons are present? The carbons are present as free carbons or iron carbide. So, its chemical formula is Fe3C. So, this is the basic definition of the cast iron. However, we do have different types of cast iron available. Now, what are those cast irons? They are grey cast iron, white cast iron, malleable cast iron, spheroidal or nodular cast iron, then austenitic cast iron and abrasion resistance cast iron. So, these are very common types of cast iron, means these 6 types of cast irons are generally used for the engineering applications. Now, these cast irons are graded depending upon, as I told you, upon the composition, manufacturing conditions, etc. It is having the different names and it has got different properties, and of course, depending upon the properties, it has it has got the different uses also. Now, we look one after another. What is the grey cast iron? Now, the grey cast iron, what you can see is that carbon here is mainly in the form of graphite. Okay. So, you know the allotropic form of carbon, that is a graphite. This type of cast iron is inexpensive and has high compressive strengths. Okay. So, that means sometimes the machine beds, etc. also can be made up, and graphite is an excellent solid lubricant, and this makes it easily machinable but brittle. Now, in general the cast irons are brittle, but of course not in all cases, that we will see. So, this type of grey cast iron are designated in the manner that has been shown over here: FG20, FG35 or FG35 SI15. Well, these are not the only 3 varieties, it is just an example how you designate an grey cast iron. Now, if you just take up the last one, that FG35 SI15, it has got a meaning that the number indicate ultimate tensile strength in megapascal. So, you know ultimate tensile strengths, if you have seen, I think you have seen the stress strain diagram. Now, normally you will be finding out the yield point, then the material goes to an ultimate stress value, maximum value, and then it goes the ruptures, okay, or it fails, or the breaking point comes. Now, in that way the maximum amount of stress that material can take up is that ultimate tensile stress, and that is in MPa. So, that this one is 35 megapascal is the strength, ultimate strength of that gate cast iron for this typical variety, and 15 indicates, as you can understand, this 0.15% of silicon is present in this grey cast iron. So, this just to give you an idea that how the grey cast irons are designated as I told you right now. Now, let us come down to this particular idea, that is a white cast iron. In this cast irons, carbon is present in the form of iron carbide Fe3C, which is hard and brittle. So, the presence of iron carbide, you can understand, increases what? The hardness, and makes it difficult to machining. Okay. So, that means in these cases what is happening, that this has got inherent hardness. So, that is the reason these particular cast irons are also called that abrasion resistance cast irons. Okay. So, that means these white cast irons we can consider as to be hard and difficult for machining. So, we should make the components where we can avoid as much as possible of machining will be better if we choose this type of materials. Malleable cast iron. So, this is one of the thing you will understand, that these are having malleability, means it can have certain a good amount of deformation, or it has a good amount of plastic zone. So, these are white cast irons rendered malleable by annealing. Now, annealing is an heat treatment process, and by which you just heat the particular material and then you cool it down, and I think it is not within this zone, but anyway, this is a type of heat treatment. You can remember that annealing is a type of heat treatment by which what you can get, you can get that malleable of cast iron from the white cast iron, and these are tougher than grey cast iron, and they can be twisted or bent without fracture. Now, these are tougher than grey cast iron. Now, what is a tougher? Means basically we will learn later on. This tougher is somewhat, you know, is a mixture of something like an strength and ductility. Okay. So, it has got a good amount of strength, at the same time it has got a stretching characteristics. That is the reason it can be twisted or bent without any fracture taking place. So, this is what the characteristics of a malleable cast iron, and it has got an excellent machining properties, and these are inexpensive also. So, you understand that excellent machining properties is a desirable situation, because if we make the machine components, then it can be machined easily. Okay. Where it is used? It is used for making parts where forging is expensive. Say for example, hubs for wagon wheels, brake supports, etc. These are made of this malleable cast iron. I think you know the word malleable, I just did not mention. The malleable means some characteristics by which you can flatten the material to a great extent without any cracks being formed. Now, these type of malleable cast irons are designated depending upon the method of processing. Say if it is made in the black earth method, then it is designated as B is black earth, M is malleable, 32 it stands for what? Just like that, the strength. Then BM 30. Now, in other way, if it is white earth malleable cast iron, then we designate this as WM 42, WM 35, so and so forth. So, these are the designations of the malleable cast iron. So, this malleable cast iron which is, you can understand, appears to be a very good material for a machine element. You can see it is having machining property and it is inexpensive also. Now, we come down to this spheroidal or nodular graphite cast iron. What is these things? In these cast irons, graphite is present in the form of spheres or noodles. So, just you can see, just by the presence of graphite in a different form makes it of a high tensile strength material, and it has got a good elongation properties. So, this high tensile strength is one of the advantages or one of the good things for which this this type of cast irons can be used very much in the machine design. Just the same way, see here the designation is ASG50. You understand AS is spheroidal graphite cast iron, and 50 gives what? As usual, it is a tensile strength in megapascal, and the second one indicates a value 7, means it is having a percentage elongation of the 7. Later on you will see that to a true ductile materials, means what we talk about, that mild steel, we will be talking about those things, will be normally having the percentage elongations much more, maybe around more than 10. Well, still you can see it has got a good amount of percentage elongation, and well, the second one do not have, it is only having a 2%. However, this SG50 by 7 or SG80 by 2 are some of the designations of the graphite cast iron, and which gives you, as I told you, the strength values and this percentage elongation. You can compare the values, see 50 and 80 quite high compared to the earlier cast irons, where we found this tensile strengths in the range of 30 to 40, 45 like that. Now, this is an austenitic cast iron. Now, what is this? Depending on the form of graphite, again this same thing, that depending upon the form of graphite present, this cast iron is classified broadly under two headings. One is austenitic flake graphite iron, another is spheroidal nodular graphite iron. One is in the flake form of the graphite, another is just as we discussed just in the last class, in the spheroidal nodular graphite form. So, all these things you can see are very well designated by the letters given by the sides of the name, means austenitic flake graphite iron. We consider one of the examples like AFG, Ni16, and Cu is the copper, then is the chromium, alright. So, AFG you understand, austenitic flake graphite, then Ni is the nickel, copper and chromium. So, others are the content, other as the materials or the other elements contained in this type of cast iron are given in the form of this nickel, copper and chromium. In the similar manner, spheroidal nodular graphite iron is A is austenitic spheroidal graphite having nickel 20, chromium 2, means you understand it is not 20, it will be as in 0.2% of the, this is chromium 2%. So, alloy cast iron contains in small percentages that I just told you, silicon, manganese, sulfur, phosphorus, all are the additive features of this austenitic cast iron. These are also as you can see, is produced by adding alloying elements for more strength and improved properties. Nickel, chromium, molybdenum, copper and manganese, these are the general materials that are used for increasing or improving the strength and the strength properties and other improved properties like corrosions, then hardness, etc., malleability. These type of austenitic cast irons are mostly used for making automobile parts. Cylinders, pistons, piston rings, brake drums, etc., all are made of austenitic cast iron. Well, you can see these are very important properties, but still we are making in the cast iron because you understand that this will be taking up the desired criteria while designing this type of cylinders, piston ring, brake drums, etc. Okay, and at the same time the components will be relatively cheaper. So that means it gives an idea over here when we talk about austenitic cast iron, that even in the cast iron you can add some amount of alloying materials to change its properties. We talk little more, although we have seen earlier that is one of the abrasion resistance cast irons, okay, but still we talk about this one separately. These are again alloy cast irons and the alloying elements render abrasion resistance. So, the designation type comes out to be again the same thing, ABR 33 Ni4 Cr2 indicates this is what abrasion resistance, 33 you understand tensile strength with 4% nickel and 2% chromium. So, these are the one typical designation of the abrasion resistance cast iron. Now, after we talk about all the things of the cast iron, now we consider another important material, that is called the wrought iron. So, this is the pure form of iron, very pure form of iron, where the iron content is of the order of 99.5%, that means it is all of iron. It is produced by what? Remelting pig iron, and some small amount of silicon, sulfur or phosphorus are present in this type of iron. And what you can see that these are very tough, malleable and ductile and can easily be forged or welded, but it has got a drawback that it cannot take up sudden shock. So, if you are using for a static or quasi-static situations, then it is really a very good material. It has got a toughness, it has got a malleability, that means it can take up toughness. As I told you, it is somewhat a combination of we will be talking about, although but at this moment we understand that is toughness means certain amount of ductility and the strength is a punched one or mixture one. Malleable, as you know, it is the property by which you can just make it thinner and thinner, and ductile, you know, it is having a good percentage elongation. That means it can elongate to a great extent in the when it is in the plastic zone. So, thereby this three properties of wrought iron makes it a very good material to be forged or welded. And you can see the uses of such wrought iron are in the form of chains, crane hooks, railway couplings and such other components in actual use. So, the use of wrought iron are really seen in actual practice to a great extent. As you can see, the very common type of machine elements are being made up of this. Now, we come down to the steel, which is one of the most important engineering materials, the steel age. You can see the improvement of the steel has taken place over the years in a tremendous manner. At this point of time, we can say that the researches and other things for making an improved steel are enormous in number. Means almost all the metallurgists are those who are dealing with this type of material properties. They are striving to make very good steels by utilizing different alloying elements, because once you can increase the strength. If we take one example, that if we can increase the strength of a material, then obviously what happens, that the dimension of the machine element reduces. Very simple idea, because a machine element is acted upon by a load, say P, and we understand if the dimension, say cross sectional area, if we consider P divided by A is a stress, in a very rough way we talk about this is the stress. So, in other way round, if we say about the dimension, it is the load divided by the material stress. So, if I increase upon the stresses, then you can reduce upon the dimensions. If you can reduce upon the dimensions, there is an tremendous reductions in what? The weight. The once you have tremendous reduction in the weight, then you get the benefit of the cost also. So, that is the reason, if possible, whenever you are using some steel on other things, then why not to use the steels of a very better quality when you talk about its strength in particular. Although the steels have some other additional properties, we will just see now. What is steel? It is basically an alloy of iron and carbon, in which the carbon content can be less than 1.7% and carbon is present in the form of iron carbide to impart hardness and strength. So, basic difference between cast iron and other things and the steel is that this is a very major one. That means the carbon content in the steels are relatively lower than what you are having in the cast iron. Now, as because this carbon in the steel is present in the form of iron carbide, what is happening, that it impart hardness and the strength. Normally, we have two categories of steel. One is plain carbon steel, another is alloy steel. Now, plain carbon steel is one which is not very expensive and it is used as a very good general purpose machine elements. Plain carbon steels. What is this? Is this particular type of steel has the properties like what you can dependent on mainly the carbon percentages. That means, the plain carbon steel property, although primarily dependent on carbon percentage, other alloying elements are also present. Now, in this case, what is the extent of the other alloying elements? It is more or less within 0.5 to 1%. Say for an example, we can have 0.5% silicon or 1% manganese, etc. That means the alloying elements are given in a low amount. These plain carbon steels are designated in which manner? It is designated as C01, C14, C45, C70 where the number indicates the carbon percentage. Okay. So, in this case what you can understand, this this designation is very unique, because you can see that plain carbon steel means it starts with an word C. Now, what are the categorization of plain carbon steels? One we call as dead mild steel, where the carbon percentage is 0.15%. Low carbon steel or mild steel as a very widely used engineering material, this low carbon steel or mild steel, which is having a carbon percentage of 0.15 to 0.46%. Median carbon steel is 0.45 to 0.8%, and high carbon steel, okay, it is having the 0.8 to 1.5%. Okay. So, more you go for the high percentage, it also having the strength and hardness also. In general, higher carbon percent indicates higher strength, and as I told you, these plain carbon steels are used in a wide range of machine elements. Alloy steel. These are the steels in which elements other than carbon are added in sufficient quantities to impart desired properties such as wear resistance, corrosion resistance, electric or magnetic properties, etc. As I was just telling you, these alloy steels are used for special purposes, okay, depending upon the type of uses and the environment, etc. These alloy steels are chosen. Of course, these alloy steels are having, as because it is having and special properties, these are relatively expensive compared to the plain carbon steels like mild steel, etc. What are the chief alloying elements? And you understand, if you just see at the slide, then you can see depending upon the type of alloying elements, it has the property of the steel changes. What are the alloying elements? Chief alloying elements as a nickel. It imparts strength and toughness. Chromium, it imparts hardness and strength. Tungsten, it increases hardness at elevated temperatures. So, tungsten steels are supposed to be one of the very hard steel, and in certain cases, you know, if you are using for small bearings of journal type, then you can use also sometimes as tungsten bearings, which really, because of its hardness, it won't wear out that rapidly. Vanadium increases simply the tensile strength. Manganese, it gives high strength in hot rolled condition and heat treated conditions. Silicon imparts high elastic limit. You understand, the high elastic limit also is an desirable property, because as long as you go to the higher elastic limit, then the deformations in the machine elements will be always within the elastic limit for even for an higher load. Cobalt is something which imparts hardness to the alloy steel. So, this you can see the nickel, chromium, tungsten, vanadium, manganese, silicon, cobalt. Well, I just left out this one. This is a molybdenum. Molybdenum also imparts an extra tensile strength. So, combination of different types of alloying elements give rise to different kinds of alloy steel. So, based on the use, environment, etc., what you can do? You can use the steels having the typical alloying elements like what I have just told. Suppose you want a strength and toughness, you can use nickel. If you want high strength, high elastic limit, you can use an silicon. Molybdenum, it can give you extra tensile strength. so on and so forth. So, the utility of the alloy steel as we understand is immense in design of machine elements. Now, this alloy steel, some examples of this alloy steel are given here. You can see that one of the situations is nickel 35 Ni 1 Cr60. So, you can understand that is a typical designations. What is this one? 35 the strength, the nickel composition, chromium composition, and so in that way it is given 30 Ni 4 chromium Cr1, then 40 the strength, then chromium percentage, molybdenum percentage, then 37 manganese 2. That means it is simply it is having only an manganese. In this one it is an chromium molybdenum steel. This is a nickel chromium steel. It is also a nickel chromium steel, but see just by different addition of the this percentages of nickel and chromium, your strength has changed. Okay. Now, one of the highly utilized alloy steel is stainless steel. So, by now it has come up as an household name to us, and all of us know that the name stainless steel. Normally, the stainless steels which are widely used in practice are called 18 by 18 steel. It's have gotten tremendous corrosion resistance property, and that is one of the thing it is highly used as machine parts. Chromium and nickel percentage are actually 18 and 8. So, that means chromium 18% and 8 and nickel 8%. So, that gives rise to the the stainless steel. You have seen that chromium, nickel and chromium properties in our earlier slide. Okay. So, what is that one? So, chromium hardness and strength, nickel strength and toughness, all these gives the stainless steel. A typical designation of a stainless steel can be something like this: 15 Si 2 Mn 2 chromium 18 Ni8. All these actually gives you the typical compositions of the stainless steel. Now, here the first word 15 is actually the percentage of carbon, which is 0.15. See, in this designation nothing have been specified about the the strengths and other things. So, once we have completed our discussion so far about the most common ferrous materials. So, what are the most common ferrous materials? Just we have learned the cast iron, wrought iron and the steel. These are the most common ferrous materials, and we have just learned that what are the different varieties of cast iron, what are the different varieties of steel, how the addition of different type of alloying elements affect the steel properties in terms of strength, corrosion, etc. Now, we will look to some of the common engineering materials which are non-ferrous metals. What do we understand? That metals which contains anything other than iron is a non-ferrous. Means ferrous, the word is iron. So, anything which do not contain iron are, but still metals are normally called the non-ferrous metals. Now, out of the non-ferrous metals, the another one, just like steel, we see in our everyday life is aluminium. So, what is aluminium? This aluminium is a white metal produced from alumina in its pure state. It is actually weak and soft, but by addition of small amounts of copper, manganese, silicon and magnesium, this aluminium becomes what? Hard and strong, and obviously it becomes usable. It is corrosion resistance, low weight and non-toxic. Now, although stainless steel are also corrosion resistance, but the thing what I can say at this moment, the use of aluminium is widely has taken place due to its one of the characteristics feature is its low weight. So, this is very advantageous in some cases where weight is a factor in design. We will be talking about this thing. Just to see the next slide. The two forms of aluminium are duralium and Y alloy. What is duralumin? Duralumin is, this is alloy of aluminium which contains 4% copper, 0.5% manganese, 0.5% magnesium and aluminium. Of course, it is the main parent element. It is widely used in automobile and aircraft components. As a matter of fact, I was just going to say about these aircraft components, which are basically based on this aluminium sort of products, because of the fact that it has to be lesser in weight for a better design, considering what? Considering the type of applications it is having, it has to fly. Y alloy is what? This is an alloy again of aluminium which contains 4% copper, 1.5% manganese and 2% nickel. And in addition to that, it is having the 6% silicon, magnesium, iron and rest is aluminium. See, you can see, although we told about there is no iron, but some amount of iron is present in Y alloy. But primarily it is a non-ferrous material. It gives large strength at high temperature. It is used for aircraft engine parts such as cylinder heads, pistons, etc. So, we can see that when we are considering about aluminium, each and every time one of the important machines in our present day life like aircraft is coming into picture. So, the reason is basically for the lightness of aluminium metal. Okay. Now, we have other one of the aluminium alloy which is called magnesium. This is an aluminium alloy with 2 to 10% magnesium. So, it is a magnesium based aluminium. It also contains 1.75% copper. Due to its lightweight and good strength, it is used for aircraft and automobile components. So, again you can see that the magnesium is also used for the aircraft components, and here it is given very clearly because it is of the lightweight and good strength. So, aluminium alloys in general have good strength and the lightweight. So, it offers a very attractive materials for machine element design. Now, we consider another very important material that is called the copper. Now, we consider some of the copper alloys. So, as I told you, copper is the most widely used non-ferrous metals in industry, and I think the use of copper is from a very early age of the machine design. It is soft, malleable and ductile and is a good conductor of heat and electricity. So, you have seen that whenever you have any machined element designed for electricity and applications of heat, then you will be finding out the copper alloys are present there. Okay. Now, brass is one important copper alloy which contains copper and zinc. It is fundamentally a binary alloy with zinc up to 50%, and as zinc percent increases, ductility increases up to 37% of zinc, beyond which the ductility falls. That means you are having some sort of this, if I plot it like this. Okay. So, that means if you are having the ductility and zinc composition, it is something like this. So, optimum value of zinc somehow or other is something around 37%, beyond which what happens, the ductility increases and then it falls. So, that is the composition of the zinc which can be around 37% for an optimum value. So, we just talked about this component, that is brass, copper and zinc alloy. Now, again what we can see that the small amount of other elements, that is lead or tin, imparts other properties to brush. What is that? Lead gives good machining quality. As you know, lead is a very good malleable material, and tin imparts strength. Brush is highly corrosion resistant, easily machinable, and therefore a good bearing material. You will be learning about the bearing. You will understand that here we talk about the journal bearing. Suppose there is some hole on a material through which a shaft is introduced and it is rotating. So, that is somewhat a concept of the bearing, which we will be talking about in details in when it comes when it finds its place. Okay. So, one of the important copper alloy is brass that we have just learned. Next one is the bronze, which is again copper, and this is SN means tin alloy. This is mainly copper and tin alloy, where the tin percentage may vary between 5 to 25%. It provides hardness, but tin content also oxidizes, resulting in brittleness. Deoxidizers such as zinc may be added. Anyway, we understand the bronze to be a alloy of again copper and tin, where the tin percentage stands to be around 5 to 25%. A gunmetal, it is also an alloy of copper, where 2% zinc is added and as an deoxidizing agent, and typical compositions are 88% copper, 10% tin, 2% zinc. This is suitable for working in cold state. It was originally, as you know, made for casting guns, but you know now it is used for boiler fittings, bushes, glands and other such uses, but the name derived as because it was used primarily for casting guns. So, now you have seen that for the non-metals, for the non-ferrous metals, we can find out the important materials that comes into picture as that is the aluminium, which has got the duralium, Y alloy, magnesium. Then we are having the copper alloys, which are brass, bronze, gunmetal. Now, we will be talking about the non-metals. But I think that whatever we have learned about in this today's class, we keep the study of non-metals for the next class. And today we know about two important metals, that is materials in machine design. One is ferrous metals and non-ferrous. So, purely non-metals and the other aspects, the mechanical properties of materials, we will be taking up in the next class. Thank you. Good day. As you know that we have been discussing about the engineering materials, and we will continue the same today. So, today's lecture is lecture number 4, and it will be again on engineering materials. Now, you see we have already discussed about the type of materials normally we use in engineering practice, that is ferrous and non-ferrous metals, and we have a discussion in the last class about this one, about all those materials. Now, today you see if you look at the slide, you can see the heading is non-metals. So, there are numerous non-metals that are actually in engineering practice. However, we will be discussing about those non-metals which are very common in engineering practice. Now, why you use the non-metals or why it finds its use in the machine design? Because one thing is that normally the non-metals are what you call it is low cost materials. It has got the flexibility, and also it has got a good resistance to heat and electricity. Now, one of the very important non-metal, that is timber. So, this timber is relatively a very low cost material, and it is a good it has good elastic and frictional properties. However, it is very bad conductor of heat and electricity. So, always you will be finding out that due to these two aspects, particularly the first one, the timbers are used in various engineering applications. Moreover, what is happening that we use timber normally in the cases of even water lubricated bearings, foundry patterns, okay. And also you will see the normal structures are also sometimes made up of timbers, and these are the major uses of timber in the machine design. In certain cases also what happens, for some temporary machine elements, timbers are also used as to manufacture timber.